And she spoke about what this question was, lots of different ways to approach it, and she gave some examples of particular structures, particular sorts of structures that would give you different answers to this question of Gromov. So I'm going to be talking today about a more general answer to this generalized question. So let's go ahead and get started. Gromov's original question was essentially, what does a typical group look like? Well, we generalize that question to, what does a typical structure look like? And let me start by talking about the sorts of structures that we want to consider here. So we're going to be framing everything in terms of varieties. So our definition of variety is going to be that for a fixed algebraic language L with only functions and constants, though I'm not really going to be talking about languages with constants at this point. A class of L structures is a variety if it's axiomatized essentially by universal equalities, we'll say. And this definition is maybe would more technically be referred to as the definition of an equational class, but really it's a variety. We're just going to call it a variety. And then if you want to talk about a presentation for a variety, that's going to be given by essentially this pair. And the first element is going to be the generating tuple for the variety. And R will just be a set of identities that we're going to say hold in addition to the more general theory of the variety. Okay. And I think later in the talk, you're going to see me use a similar bit of notation, A bar R in angle brackets. And that's going to give us the structure so that the identities true in the structure are those that are going to follow logically from the identities in R and the axioms for V. Okay, so now that we have that, we can talk about how to formalize this question. So here we're going to say, well, consider some property Q that would make sense in the context of this variety. And let's let PS be the number of presentations in which the relators, those identities that I discussed before, have length at most S. And here I'm going to take the length of a relator to be essentially the total number of function symbols. Oh, okay, I just realized, yes, you can see me very small next to my slides. So if I make hand gestures to try to explain things, it will work. Okay. Okay, so PS is just the number of presentations in which the relators have length at most S. It doesn't make sense to talk about all presentations. We need some reasonable bound here. And we're going to say PS of Q is the number of those presentations in which the resulting structure actually has the property we care about. And then we can say that the limiting density for this property is the limit as S goes to infinity of the ratio of structures with property Q and presentations of length at most S to the total number of presentations where the relators have length at most S, if such a limit exists. And on Monday, Julia showed some cases where that limit doesn't actually exist. So this is actually a necessary thing to say. And now that we have that, we can talk about what it means to be a typical structure. We're going to say that a typical structure has property Q if Q has density 1. So Q only essentially fails on a set of measure 0, we'll say. Okay. So here's the context for today's talk. I'm going to be talking very specifically about a certain form of variety. So let's just take L to be a language with finitely many unary function symbols, F1 through Fn. And we're going to take V to be an algebraic variety, and we'll say its theory is T. Then we're going to say that V is a generalized bijective variety if for every function Fi, from T, you can deduce that, well, each Fi is injective, each Fi is surjective. Okay. And V is going to be a commutative generalized bijective variety if the axioms further imply that for any X you look at, the order of application of Fi and Fj doesn't really matter. Fi of Fj of X is equal to Fj of Fi of X. Okay, so these are the circumstances I'm going to be talking about today. And the result we're going for is essentially this one. If you have such a commutative generalized bijective variety V, and you have presentations with a single generator and a single identity, so pretty much the simplest situation you could imagine being in for the presentations. Obviously, you would like to have a generator, and if you don't have an identity to work with at all, life gets very dull. But for such presentations, the 0-1 law holds. So what do I mean by that? I mean that the density of any sentence will be either 0 or 1, so never undefined, never intermediate, and the sentences with density 1 are going to be exactly those that are true in the free structure. So I just realized I'm talking about the density of a sentence being 0 or 1, where previously I was talking about the sentence, a property having density 1. Often we'll conflate a property having density 1. Well, we'll just write down a sentence that describes that property, and we'll talk about the limiting density of that sentence instead. Okay. So this is where we're going with this talk. And this talk is going to use some kind of interesting structure. We're going to need to build a little bit in order to actually prove this result. And one thing that we're going to need to come up with is our own version of Gaifman's locality theorem. And the standard version says that any formula in a relational language can be expressed as a finite Boolean combination of, quote, local formulas and sentences. Well, we actually proved a different version of this because we wanted to be in really good control of what these local formulas and local sentences were. So I'm going to kind of talk us through the proof of our version of this before I get into just using it as a tool to prove the main result. Okay. Oh, I should also comment that after Julia spoke about some of this work at the retiring presidential address in April at the Cornell ASL meeting, I had the pleasure of meeting Gaifman, who expressed to me that he was very glad that the young people these days were using the ideas that he had developed. So Julia and Turbo and I were all very flattered. So let's start talking about how we do this. So the first tool we need here is that of a Gaifman graph. So what's this? Well, if you have a structure, then the Gaifman graph of that structure is going to be an undirected graph with that same universe, such that there's an edge between 2 points exactly when one of the functions you have in your language will take you from one to the other. And you can see that this is a way of helping us build up terms, essentially, right? You want to build some term based on some element of your structure X. Well, you just start building the Gaifman graph. So you take, well, f of each, you take f1 of your X, you take f2 of your X, so on and so forth. And then you can extend your graph. You can take f1 of f2 of f3 of your X, so on and so forth. And as we look at this Gaifman graph, we get information about what maps to what. Are there loops, for instance? Do we have a bunch of rays shooting out from one point? How many connected components do we have? And the notion of connected components is honestly going to be the most important thing for us here. So we're going to define an equivalence relation on this structure such that X and Y are equivalent if they belong to the same connected component of the structure's Gaifman graph. So if we're thinking about this more syntactically, really what we're trying to say here is that X and Y belong to the same connected component if we could construct a relator that would have X on one side and Y on the other. Okay. And I'll just point out that the structure is going to be determined up to isomorphism by the number of connected components of different isomorphism types. Okay, but we're concerned about the length of the relators, right? So let's talk about how we measure distance in this context. So let's just let the distance between X and Y be the least R such that there's a path of length R from X to Y. So in other words, how many applications of these functions do you need to get from X to Y? Obviously, if there is no such R, we take it to be infinite. But then we can say, well, we can talk about neighborhoods. So let's take some element of that structure. We can talk about BRA. That's just everything in A that's within distance R of our original point. And then we can generalize that to tuples. So if we have an n tuple from A, we could just write BR of that tuple to be the union of all of the R balls around the individual elements of that tuple. And then we can use the notation B infinity A or B infinity A bar to give us the relevant connected components. Okay, so here you can see we are taking the Gaifman graph and we're using it so that we can think about essentially how long is a relator here? What is the distance from one to another? Okay. So now that we have this notion of distance, there's a set of formulas that's going to start coming up over and over. And these formulas, well, what are they really doing here? Well, for each R and each N, so what are the R and the N doing? R is essentially being a distance, as we had in the previous slide. And N is going to be the size of the tuples that are plugged into the formulas alpha X. So what are we asking for them? Well, take any structure in the variety. Each N tuple from that structure is going to satisfy a unique formula, alpha X in this set, CRN. And for any two structures in this variety, if we have N tuples, A and A prime in these two different structures that satisfy the same formula in CRN, then we can find an isomorphism from BRA onto BRA prime that takes A directly to A prime. Okay. So if you think about what they're doing, basically they're just describing the possible, think of it as substructures, BRA, for the N tuples A for all of the structures in this variety. Basically, if you have this variety, what could a ball of radius R look like around any point, around any 2 points, around any 3 points, so on and so forth. And I'll also just kind of quietly say that we could take the formulas alpha to be either existential or universal, right? We could just say that they're expressing that there is a Y that corresponds to possible elements of this ball of radius R. With this particular atomic diagram, universally, we could say that for all Y corresponding to these possible elements, BR has this particular specific atomic diagram. So we actually have some control over how complicated these formulas are. Okay. So really, please just think of them as describing possibilities for a ball of radius R. All right. So we need to talk a little bit about locality. So these CRNs are going to give us our R local formulas. And then our R local sentences are essentially going to be, well, let's look at the second component first. We could just say there is something essentially whose R ball looks this particular way around that point. Or number one, I suppose, is the more complicated one. Here we're just saying that there are some elements, each one of which specifies a particular alpha I. And then we're also going to say that the distance between any two of those points has to be bigger than 2r. So we're not technically saying that they're in different components. We're just saying you can't get from any vi to any other vj by applying, say, only 2r function symbols. Okay. So here's our local formulas and our local sentences. And then, of course, we just say that a formula or sentence is local if it's R local for some R. So in other words, if it's defining an R neighborhood, or if it's talking about or if it's talking about elements that have specific R neighborhoods and aren't close together. Okay. So what does our version of Gaifman's locality theorem end up looking like? So first of all, any elementary first order sentence is going to be equivalent over T to another sentence that's a simple finite Boolean combination of local sentences. And then the second part is really something very similar for formulas, except we're actually saying what the formulas are going to look like. Any elementary first order formula phi with free variables x is going to be equivalent over T to a formula phi star x that's a finite Boolean combination of local sentences and local formulas. And we can, in fact, specify what those are. Like I said, phi star is going to be a finite disjunction of formulas of the form alpha I of x and beta, where alpha I is going to be one local formula and beta is going to be some finite conjunction of local sentences or negations of local sentences. Okay, so this is what we're going for. So how do we get there? Well, this is where I say I looked back 10 years to the 2012 CCR. I'm going to look back 10 years before that and say that when I was an early graduate student, I thought I might become a model theorist. So 20 years on, I'm somewhat laughing about the way life can come circled again. So let's talk about theories and types. So just some terminology up front, and then some things that seem very natural afterwards. So if you have a structure in your variety, its local theory will just be the set of all local sentences and negations of local sentences that are going to be true in A. And for any tuple from our structure, its local type will just be the local theory together with the set of local formulas that are true of that particular tuple in the structure. Okay, so basically all of these lemmas really are going to fall out of the fact that we picked our local sentences and local formulas very carefully. So what's the first one? Well, take two elements of the two structures and the variety. Well, if you've got n tuples, A and A bar, respectively, from the structures A and A bar, and they satisfy the same local type, then we can find a partial isomorphism from the connected components of the first tuple to the connected components of the second, such that A is mapped to A bar. Essentially, like I said, we defined CNR to make this work. And then the next lemma is, well, now let's suppose that those two structures in the variety are saturated and have the same cardinality. Well, if they satisfy the same local sentences, then they're isomorphic. And this really just comes down to the fact that the isomorphism type is determined by the number of connected components of their isomorphism types. And that if you have an infinite saturated structure, the local type is satisfied exactly when it's finitely satisfied. And then we can just reduce this to information about the alpha R's. Okay. So then what else do we end up using here? And you might have noticed, really, I'm giving more of an ingredient list for each proof than the full proofs. It's Julia got the example part of the talk. I'm getting the technical proof part of the talk. If we had each taken a technical part of the talk, first of all, it wouldn't have gone as well, but also we could have given full proofs if we'd split up the technical part. But I don't think you would have been as interested if Julia hadn't explained why we care and some examples in the first place. So we're doing an ingredient list basically today. Okay, so here, let's say a little bit more about local theories. If they have the same local theory, they're elementarily equivalent. Well, we just take that common local theory, take two saturated models of it of the same cardinality, apply previous lemma. And then, well, if you've got two n-tuples from the same structure in the variety that satisfy the same local type, then there's an automorphism of the structure that takes A to A bar. Honestly, you just say, well, if they satisfy the same local type, then their connected components are isomorphic. And then you extend that partial automorphism to a total automorphism just by mapping, just by taking the function to be the identity off those. Okay. So after working our way through all this, the work for Gaifman's locality theorem felt a little bit strange to write down, right? The lemma is just that if a sentence B, here I'm doing the sentence form first, then I'll do the formula form, but all the ideas are really in the sentence version of Gaifman's locality theorem. So here, if A models some B, then there's another sentence that's true in that structure that is a finite conjunction of local sentences and negations of local sentences, such that from T, you can deduce that psi implies phi. Well, okay, this really, as I was writing my talk, started to feel very much like something you might give your upper division undergraduate logic students, right? You just take the local theory of your structure. You say that, well, take your theory of the variety T, take that local theory of S. And if you take their union, certainly you can deduce phi from that. Well, then, okay, you just take a finite subset of that local theory and take the conjunction of the sentences in it to be your psi. And then the proposition just requires us to reverse that a little bit, but it has very much the same flavor. Okay. So what about the formulas? Well, honestly, it seems to work very much the same way, except you work with saturated models. You take your tuple of variables, you replace them with new constants. Congratulations, now you have sentences in an expanded language. Reduce, you're fine. Okay. So this is one of the tools we're going to need. So now I can start talking about halfway into this talk or so. I can start talking about the theorem that Julia and Turbo Ho and I ended up getting out of all this. So here we go. Take your, and I mentioned this before, but take V to be a commutative generalized bijective variety in this language with finitely many unary functions. And we're going to consider presentations with a single generator and a single identity. So again, kind of the nicest set of presentations you can imagine. I'll explain later that really we could do this with more generators. And once I go through the proof of this, I'll be able to explain why we can do a little bit better. But okay, so let's let F be the free structure on A. And then if F is infinite, then the sentences true in this free structure will have limiting density 1. Okay. So what do we need to get here? I've talked about the Gaifman graph. Let me talk about the Geisman group. So what are we doing here? Well, take your generalized bijective variety. We have two ways. We have a way of saying the two strings of function symbols, which I'm probably just going to start calling terms, but two strings of function symbols, t and t prime, they're equivalent if you can deduce from phi that for every x, t and t prime will apply it to x and you get to the same place. Okay. So then what do we do to get the Gaifman group? Well, we take the group GV consisting of equivalence classes of these strings of symbols. So two sequences of strings that get you to the same place, same members of the same equivalence class. And then what's the operation? Well, it's just concatenation of strings. So this group is going to have a natural action on the free structure generated by any tuple A. I suppose I really don't need a full tuple here, but so it goes. Because what does it do? You take your group element, you apply it to your tuple, and congratulations, now what's the outcome? It's just whatever you would get by applying that string of function symbols, that string of functions to the tuple in the free structure. And then formally, if I wanted to talk about the orbit of B under this group action, I could just say that it's the set of all x such that for some t in the Gaifman group, TB equals x. Okay, really, what is it? That's just the set of elements that are generated by B, as I think is maybe a little bit less formal, but also for me a much naturaler way to think of it. Okay, and I guess I should just mention for bookkeeping purposes here that if B is a generalized bijective variety, then it's, we actually went through and showed that if you have a free structure generated by a tuple A, then this action on the free structure is well defined. We can work with this with impunity. All right. So how are we going to use this? Well, I'm going to, before I start using this Gaifman group, I'm going to just go back and make some observations about CR1. It's very tempting actually to drop the 1 and just say CR. We're talking about a situation where we only have one generator. So somehow this feels kind of natural to talk about CR1. Okay, well, let's take any terms, we'll say U, V, and W in the Gaifman group. Well, what happens? Well, you can see from T that for all x, u of w of x equaling v of w of x, well, that's just equivalent to u of x equaling v of x. And if we have an element of CR1 and we have an element of the Gaifman group, then T will give us that for all x, alpha of w of x will hold exactly when alpha of x will. And then the next lemma essentially says the type of quantifier you have is not so important. And the general idea here is that if you have one generator in a situation like this, all the elements are going to essentially have the same local type. May I stop and ask a question that only happens in remote talks? Is the cat yowling outside my door audible to anyone but me? No? Okay, thank you, Julia. Okay, in that case, we're going to carry on. My research assistant has done her job for the day. She can sit outside now. All right. So this is just saying something a little bit nice. Oh, hold on. Thank you, Veronica, too. Okay. All right. So that's just a little bit of just kind of some quick notes about things we can say about these special sentences, well, these particular local sorts of sentences and formulas. Okay. So what are we going to take as the, I think in our paper, we're just calling them important sentences, and I rather like that, so I'm keeping it for this talk. What are the kinds of sentences we're really going to need to consider? Well, the ones that say that there is going to be some element whose our neighborhood looks a particular way. And then this is also going to feel familiar. The statement that there are at least n things such that the distance between them is more than 2 times r. And I'll just comment quickly that if you have a statement of the second form, you can actually get that from a statement of the first form that is true in the pre-structure. So essentially, how does that work? Well, it would be true in a saturated model. You take witnesses to it, and then you find a ball big enough to hold all the witnesses. Okay. So just kind of keep in mind, we're going to need to know what neighborhoods look like, and we're going to need to be able to talk about there being things that are far apart. Okay. So let's talk a little bit about what this Geisman group is going to look like, because now we're getting back to that. And it's going to become very important for us to know what kind of group this even is. It's going to be abelian. It's also going to be finitely generated, given the sort of variety we're looking at. Well, what does that mean? It's a finite direct product of cyclic groups, and let's say we have generators B1 through Bk. Well, okay, since it's infinite, we must have some Bi that has infinite order without loss of generality, let's say B1. And if that's the case, it's going to generate a copy of Z. And now what we're going to do is we're going to look at a projection of an element on the subgroup generated in that way. And this is where my shall we say, non-pure logical, I suppose, talent, interest, what have you, comes in. We're going to consider this projection as a random variable. So what do we want to say about this projection? Well, just keep the random variable thing in the back of your head for a while. But I want to do a little bit of bookkeeping first. So what's the bookkeeping? Let's take the max of the absolute values of all those projections of just the original functions in the language f1 through fk. Let's just take their max. And then we can just say that, well, let's say that our term t has length at most r, then, well, certainly the projection of t is going to be an integer and it's going to be bounded by, well, at worst, it's r times that maximum. And then we can say that, well, we're going to be interested in something of this form, ta equals t prime of a. And if t and t prime both have length at most r, then how far apart can they be? Well, no more than 2r. And that means that the difference between their projections is going to be bounded by 2r times e naught. And it turns out that it's going to be enough to show that if the statement ta equals t prime a or ta is not t prime a is true in f, then that is going to have limiting density 1. Okay. So how is this proof going to go? Well, we're going to need to take 2 steps here. Oh. I'm given to understand that the cat is in fact audible. I believe that I have a partner who's taking care of that right now. Okay. So what we need to show is that for a fixed k, the set of presentations, remember we're looking at presentations with a single generating element and a single relator. So we want to look at the set of presentations such that if we consider our relator, then that corresponding absolute difference of their projections is less than k, then that set of presentations actually has limiting density 0. And then the next bit feels more technical. For a fixed k and a fixed identity r of this particular form, then, well, suppose that that difference is not less than k, but bigger than our particular e naught times k, then if you have a u and v such that the distance between u and v is relatively small in the Gaifman group of the free structure, then the statement ua equals va will hold in the free structure if and only if it holds in this particular presentation. Okay. So I suppose the next bit of bookkeeping we're going to need is that sometimes it will be simpler, more straightforward, if instead of talking about an equality where you have a non-trivial term on each side, right? T of a equals t prime of a. Well, sometimes it's going to be easier if we could just find an equivalent equality t star of a equals a. So let's just take that one. It'll be useful later on. Okay. Oops, sorry. Okay, so how do we do step 1? So I am going to kind of talk my way through this a little bit. So the lemma we need to do this says that, well, take any k you like. The limit, basically the limiting density of this property, that the difference of those projections is less than k, that does have limiting density 0, which will in fact give us that for any k, the set of identities where this is big has density 1. Okay, so let me maybe talk my way through how this proof works. I've got time for this. Let me talk my way through how the proof works. I wrote some fun probability calculations involving the central limit theorem. So it's not entirely clear how the central limit theorem is going to come into this, because what is the central limit theorem for? It's for a sum of IID random variables, or it's for a mean of IID random variables. So where does this come from? Well, it comes from the fact that if we look at these two projections, they're not actually independent. So we don't want to just think about a new random variable generated by their difference, because thinking about the difference of dependent random variables is maybe more unpleasant than we really want to go through. But if they're not independent, what we can do instead is we can condition on the length of one of the terms, because here we know how long those relators could possibly be, condition on the lengths of those terms, and then average out all of those resulting conditional ones. And when you do that, you have the sum of IID random variables you need to apply the central limit theorem. I guess I should also say really quickly that in the proof, we don't actually technically use PS here, because remember, PS is the set of presentations given by relators of length less than or equal to S. We actually use P equals S here, where we're looking at presentations where the relators have length exactly S. And there's some bookkeeping to be done to be sure that we can do that, but it's just some nice little combinatorics to see that looking at the ratio of PS of a property A to PS and P equals S of a property A to P equals S, in this circumstance, we really can just work with P equals S. That makes our life a lot better, really. Okay. So, right. So here we, so here we were able to do a little bit of work and get around this dependency in what I think is kind of a cute way. All right. So then let's remember what step 2 is, right? Step 2 is going to be for a fixed K, for a fixed identity. If instead this difference turns out to be large, then if that's the case and we have terms U and V that are very close to each other, oh, that's in the graph, yes, then we can say that the free structure says that those are equal exactly when this particular presentation says they are. Okay, so how does this work? This one is, let's say, more algebraic. And what does this involve, though? What are the components? It's going to take calculations on the projection of U, the projection of V, and some, let's say, projections of very closely related things, as well as a technical result on cosets of that T star. Remember, T star of A equals A holds exactly when T of A equals T prime of A. So T star of A is just our way of reducing our original relator to something of a form that's a little bit easier to work with. And this technical result is where we need the Gaifman group. Okay. All right, so finishing the proof. We take these things and it really takes a couple paragraphs to finish once you have all this. So for any integer, the set of identities such that this is big, that's going to have density 1. And then what do? We take some fixed sentence, we take K so that both of them are, all of those terms are relatively short compared to K, and that they're still rather close to each other. Just keep going, you'll find it. And then the sentence will hold in the free structure exactly when it holds in the structure given by identities of this form, where this is big, and this has density 1. Okay. All right. So maybe let me talk a little bit about how we could extend this to a case with, let's say, more generators. Well, essentially, there is a multidimensional central limit theorem, and you can use that in any situation where you have a commutative generalized bijective variety, such that you don't just have Z embedding in its Gaifman group, you have, say, Z to the K embedding in that Gaifman group. Okay, so here, oh, sorry, that would give you K identities, sorry. So here, if you've got, in this case, if you have one generator and K identities, that would satisfy our 0-1 conjecture, and the limiting theory would agree with that of the free structure. Yay. On the other hand, if ZK does not embed into the Gaifman group, then this won't work. You can come up with some nice counterexamples. I think Julia actually presented one of them on Monday, yes. You can find a bijective structure with a function symbol for, say, S, think of it as successor, and a function symbol for S inverse with, I believe, 2 random identities. And that would be a situation where this wouldn't work. And this is kind of why, because ZK would not embed into the Gaifman group. Okay, I think I've got a couple more minutes. So what can I do in that couple more minutes? I'd like to maybe give you just one case where the 0-1 law fails. And we can maybe think about the contrast of this situation. So let's take a language, at least 2 unary functions that include, say, f, and let's take a variety such that for some term t that has a symbol that isn't just f, the theory says that contains the sentence for all x and y, t maps x and y to the same thing. So essentially we have some constant here. And then let's take presentations with an n-tuple of generators and a single identity. And if in the free structure, f of this term of A is not equal to simply that term applied to A, then the 0-1 law fails. We can find a sentence with limiting density that's neither of the above. So I realize that this is my second to last slide, and maybe it's not a great thing to have that called a quick discussion of failure, but I would like you to remember all of the preceding successes. So what goes wrong here? So what's the sentence in question? Let's just think about the sentence for all x, f of that term of x is equal to that term of x. So basically, plug that term in, you get it out whenever you apply the other function, the function f. So A just has the set of identities of the form essentially t of, let's say, u of A equals f of t of B. And our f is going to fix the constant value in those structures. So our sentence is going to be true. But if we just take for B the set of identities of the form that just say t of this thing equals t of that thing, well, that's not really additional information. The resulting structure will be free. F doesn't fix the constant value because it's not obliged to fix the constant value. So that sentence will be false. And then all we would do would be to show that neither of these sets of identities, and thus neither phi or not phi, will give you density 0. And I think I've gone on for a minute or so longer than I'd intended with that. So I think at this point, I will simply say thank you for your attention and for being good with me talking so very, very fast this morning, afternoon, what have you. I want to know that it's very strange to look at an auditorium full of people applauding from high up in the back row.
Thank you. Any questions for Johanna?
I know it's the
So
last full day of the conference. It's a long day.
I have a very basic question. Could you go back actually to the slide where you first start talking about I think it was called the Gaifman graph?
Yes, good. No, forward. There we go, yes.
Yes, I was just trying to understand this graph by way of some examples. And I was curious about an example where there were two functions f, and I guess one structure where the two functions are actually the same function, and another structure where the one function is the inverse of the other function. And I was trying to understand if the graph did something different for that example, and if it should.
Okay, let's think. Okay, so what's it going to look like in the first case then, right? You take, I mean, I guess the question is how many generators do we have? Let's say one, make our lives easy. So then in that case, you're just going to start applying f to that generator.
Sort of in both directions.
Yep, yes, so chain, yeah? Yeah, so, okay. So I think this might be the point where I say that if you don't have the inverse, if you don't have an explicitly named inverse function, and this is something that I think Julia and I both fluffed over in our talks, I'm sorry about that. But if you don't have a named inverse, then there should be a term, then there actually will be a term that functions as the inverse, yes? So, yeah, so, right, so would those graphs be different? Julia, I'm not seeing that they would. Am I missing something really obvious this morning?
Let's see, so if I had answered the phone just now,
Of course.
I sort of lost it, but so you have do you have a bijective, do you have the bijective axioms?
I'm assuming we're talking about a commutative generalized bijective variety like we have been. Is that correct, Linda?
So if we have that, then
I'm thinking of,
always
yes.
is a term that names the inverse for each fi.
Yeah.
So let's see. So the two structures were the one where you had, let's see. So you were saying that one function is the inverse of the other. You had an identity that sort of said that. I've had identities that said that somehow.
And in the other one, you have something explicitly stating that they're the same. Is that it, Linda?
That the two are the same. So
I think I'm also a little bit turned around when we're just talking about a structure and its Gaifman graph, or when there's a theory also around. So you're talking now also about additionally a theory, and I think that I've missed how the theory is related to this situation. So I was just thinking of two structures, one where the two functions are just the same function, and the other where the one function is the inverse of the other one.
Okay, right. So whenever we talk about a structure, we're thinking of a structure in the context of some sort of underlying variety. And the variety comes with a theory of its own. So
So there's-
actually, the Gaifman graph, the notion of a Gaifman graph, that makes sense regardless.
yep,
And if as long as we have this, so we're thinking of the language is fixed,
right.
FIs. Okay, and there, if you actually think of the successor function with its inverse as one of your two structures, and the one where the two functions are the same. So if the two functions were the same, so you would get starting with one generator, I guess we're still thinking of one generator, you would get
The Z chain.
you would get just an omega chain.
Oh, right.
Two
Yes.
functions are the same.
Mhm.
If the one is the inverse of the other,
Then you get
you
Z.
get a Z chain.
Yep.
So they're chains, but they're not the same Gaifman graph.
Yeah.
And you would see that difference.
Right, because if you don't explicitly have the inverse as you go through building the Geisman graph, then from your, say, your one generator, you're going to be able to map only forwards. But if you know you have an inverse, you can map backwards from it as well. Are my hands going the right direction? You can map backwards from it as well.
Yeah.
So there are a few people now in the room who are wanting to say some things. So I'll
Bring it on. And also, if you could tell us who's speaking, that would be nice. You're all very small in the Zoom window.
Okay, so waving. Sorry, can't say my name right now. I'm too tired.
I know.
I mean yeah, thank you, Julia. I mean the structure is just whatever the structure is, right? So we don't need to be thinking about generators and stuff right now.
No.
And if it's
Right.
the
Right.
sort of if it's the same structure, and if we're just sort of deciding what kind of functions we are naming, then just by the sort of just by the very symmetric nature of how the edges are defined, it should just follow that basically if you have a function that has an inverse and then you add the inverse to the language, the graph doesn't change because you've already put in all of those things anyway. On the other hand, adding another name for the same function also shouldn't change anything. And going by what's written here, it should definitely be the case that that you do get the very same graph and the situation in the
So, but knowing that you had an inverse assumes something about the structure that we weren't necessarily assuming in the definition.
Yep.
So if we had one of these
There was
bijective structures, well, saying that Fi is its own inverse, if we actually use that same name for the inverse, say that name, well, it means you have a structure that's just, it's a one cycle.
can I suggest that we continue this conversation after the talk?
Whatever that means when some of us are remote, absolutely.
Awesome. Does anybody have any other questions? All right, let's thank Johanna again.